Greetings to our committee and advisor. Our group is going to present about the potential of using microbially induced calcium carbonate precipitation (MICP) for the ancient Masonry foundation. The organizer expects to use all the civil engineering knowledge in the preservation of the ancient sites, but the ancient site is under the authority of the Fine Art Department for act on the structure or conduct activity that has impact on it by producing the vibration or employing the chemical method that has impact on the region surrounding the ancient site. As a result, there are the numerous constraints in terms of the maintenance. But nowadays, there is the alternative technology to help improving the soil quality, including the porous structure, microbially induced calcium carbonate precipitation, or MICP. Is a biotechnology using increased soil strength by the bacteria that can produce the calcium carbonate from the enzymatic degradation of the urea. The resulting calcium carbonate to fulfill the void between the soil particles for the compaction to react with the carbonate ion, which is also product of the bacteria, and finally they combine and precipitate as a calcium carbonate, as a question is shown in the slide. Apart from applying MICP technology to improve the soil quality, MICP has recently adopted to some kind of structure of building, such as the roof tile or the ancient wall treatment. But there is still no application to the foundation, and has previously been no research into the coexistence of the local microorganisms that may affect to the activity of the MICP process. Therefore, our project expects to the possibility that the use of MICP technique can be applied to treat the ancient foundation by using the calcium carbonate to fill the pore and expect that the masonry performance will be increased. The objective to apply MICP technique on the foundation of historic structure, and to investigate the effect of local microorganisms in the local soil on MICP effectiveness. Scope of the research: the local sand from the site near the historical monument site in Thonburi, and the ancient bricks are made by the cutting masonry brick into 5 x 5 x 5 cm of the dimension. The ancient mortar refers to the mixture suggested from the milk proportion that has been certified by the Fine Art Department. The microorganism used in the research is Ricini-Bacillus sphaericus strain LMG22257, which is found from the past study that it can produce the carbonate. And the last, the compound and the chemical reaction arising from the improvement are investigated by scanning electron micrograph analysis, or SEM, and energy dispersive X-ray spectroscopy, or EDS.
Before launching the experiment, this is the step to choose the type of microorganism. A Bacillus sphaericus LMG22257, or that we will call GAN, was chosen to be culture for MICP. The reason is that this strain has recently been utilized to induce calcium carbonate precipitation in the construction field, due to the ability of releasing high urease enzyme within a few hours after incubation. And here is the class that shows the reproduction ability of LMG22257 in terms of OD600, which is the optical density of living and non-living bacteria measured at a wavelength of 600 nanometers and measured by spectrophotometers. So we can notice that every increasing hour of incubation, the density of bacteria is increasing and entering the stationary phase between 12 to 18 hours. However, this bacteria is commonly used to produce the enzyme urease for MICP. So, the concentration of the urease test was prioritized to set up the most effective urease activity conducted by only living bacteria. The objective to test the urease activity is also to choose the best incubation hour that the bacteria can release the highest enzyme. By controlling the optical density value at 0.5, to ensure that the density of bacteria remains consistent during every incubation period. The urease tilt between 12 to 18 hours is highly intensive as indicated in the picture, and has the same relevance with OD600 in the previous slide. So we decided to choose 12 hours of incubation as the suitable operating time of twice daily treatment for 18 days. To imitate the ancient Masonry, we prepared a sample that had non-perfectly cut brick with the surface detailation and mortar samples, then embedded in the sand derived from a site near historical wall in Thonburi. The local sand will be separated into two cases. Case 1, the local sand that was sterilized at 121 degrees Celsius, and Case 2, the local sand that remained the same condition. The reason is that to see how well pure stain LMG22257 performs on sterilized sand without any local bacteria, and compare the result to the local bacteria working with LMG22257. Additionally, to treat MICP, we must combine the water, chemical solution, and bacteria in a single container for the reaction, and this causing the performance is difficult to evaluate due to a variety of factors. So we divided the container into three conditions, which are MICP treatment, pure chemical soaking, and water soaking. After 2 cycles of treatment a day for 18 days, we could see that calcite appears on the surface of both local sand and sterilized local sand at about the same level. It's possible to conclude that LMG22257 can precipitate calcium carbonate and works well with local bacteria. The additional result is on chemical soaking condition. There was an appearance of calcite on the top surface of local sand. In contrast, mineral precipitation was not visible on the top surface of sterilized local sand. This implies that the bacteria living in the sand near a historical wall in Thonburi have the potential to produce calcium carbonate when soaked in a chemical solution. For soaking water condition, there is no mineral appearance. It was only used to study the effect of water on MICP samples.
As shown in bar charts, where dark green show values before test and light green show values after test, that samples submerged in water have decreased densities and increased porosities. In the other hand, samples submerged in MICP have significantly increased densities and porosities when compared with samples submerged in water. So, the results show that MICP helps to increase densities and contributes to slow the increase of porosities in bricks and mortar. Calcite sedimentation on the surface of samples after MICP process can verify by using scanning electron microscope or SEM. As you can see in two pictures above, calcite elements are seen on the surface of samples submerged in sterilized sand and local sand. So the samples of sand were taken to verify as well, and it showed that sand have calcite elements along the surface too. So, energy dispersive X-ray spectroscopy, or EDS, was used to determine weight percentage of calcite. The results show that the samples submerged in MICP local sand have higher value of weight percentage of calcite than samples submerged in MICP sterilized sand. These pictures show calcite elements on the surface of the samples submerged in MICP local sand in both before and after test. Then the samples were taken to measure different surface height after test by average level of surface of each sample and measure the different height from reference box. The results show that All samples had average height increase of 1,000 micrometers or 1 millimeter.
For the conclusion, compared to untreated samples, the bricks and mortar that were treated show outstanding less porosity, so it confirms that MICP can be used to improve the potential of ancient structure. An MICP treatment sample in local sand is outstanding when it compared to sterilized sand, also confirming that the effect of local microorganisms is effective. Thank you for your attention.